services, and industrial. And basically what his company's about is high performance. This is used with to deliver human performance improvements. Build the ability of an individual or system to execute a task efficiently and effectively. Generally, a good performance characterized by high speed, accuracy, and consistency in achieving the desired results. It can be measured in various ways, and I'm sure he'll go into that sort of understanding and expose us to what he's about. So if you're ready, Ian, it's all yours.
Okay, thank you. So we'll start today with a little introduction. I'm going to talk a little bit about some successes we've had in the pulp and paper industry. This is a letter from the site director at Beauregard, and I think it's a good example of what people should be anticipating when they're doing a high performance improvement project. And as you see from the letter here that's posted, it says from the period of 2008-2010, Beauregard totally changed its control room system. Originally, the site was managed by 16 different control rooms, and this was remanaged into one common control room. The site manager was told by all of his colleagues in the industry that a central control room would not work in the pulp and paper industry, and that he was wasting his time and money. But he had the willpower to go ahead, as they were struggling trying to recruit people, and they couldn't man all of their posts. And the average age of their workforce was around about 62, so there was a very large number of people coming up for retirement. So it was a big problem. And it points out here that change was done in close collaboration with user-centered design services, and the end goal for Beauregard was to achieve safer operation and increase productivity. That's volume, quality, and staff. The original way of controlling the site led to a lack of communication and misunderstandings that affected safe operation and reduced production. He goes on to basically say that the cooperation went long after the building of the control room and until a new culture had been established on site. During this work period, the TRIs went from approximately 6 down to 1. The sick leave went from 8% down to approximately 4%, and the volumes increased with approximately 5%, and the hit rate increased to around about 10%. Beauregard had an aim of lowering staff and achieved its goal of lowering staff by 30%. And again, he's posted here that basically the annual savings was over $10 million a year, and that's a great project. And so basically, I raised that as to set expectations that basically, if you do this project right, you will make a big difference to operators and to the performance of your facility. We introduced at the time what we call our 6-step methodology, which starts out with understanding that how many operators you actually physically need and making sure that none are overloaded, and also deal with positions that are underloaded. Alarm management is the next piece of the circle. And again, it's about rationalizing the alarms and meeting the NIMMO KPIs. And then thirdly is the HMI, and we used to call it ASM graphics, but ASM got a very bad name and got known for being blob graphics. So trying to get the industry to understand what we were really talking about, I changed the name to high performance HMI. And then basically we look at screen layout, screen viewing angles, sizes of screens, and basically how many screens you have on a console, and then basically how do you provide overview screens. So again, there's the next section was the console, and then it rolls into basically the control room design project. So how do we get there? And first of all, we've got to look back a little bit of history. And when I started in the industry, basically this is what a control room looked like. And basically there was a limited number of alarms based on the number of windows that were available on the annunciator panel. And if you wanted to add a new alarm, the question was, well, which one do you want to take away? It wasn't simple like we have today with the DCSs, where we could just have hundreds of thousands of alarms. And we've seen the consequences of that, out of control alarms. And so today we have good guidelines and an ISA standard, SP18, which is used to address alarm management. And that's part of our circle of influence as well. As we introduced technology, we basically went from those panels on the plant control room to faceplates on a DCS system, and operators managed to run with 8 faceplates. And it was a limited view of the process, but the operators were extremely good and extremely fast at controlling the plant, even without a diagram. And that, which leads us to the question, how much information does an operator physically need in the diagrams to be able to control the plant? And these are a good example that they could do it with just faceplate controllers. And they had hundreds of faceplates, unfortunately, and often had navigation problems trying to find them, which we resolved by adding graphics. So one of the experts in this topic of human-machine interface is a man called Ben Schneiderman, and he once said, a picture is worth 1,000 words and an interface is worth 1,000 pictures. So I want us to think about that as we go through this presentation. An interface is worth 1,000 pictures, which is often what we see as we reduce the number of graphics on projects to around about 30% as we go to high performance graphics. Of course, the saying is a little bit of a historical comment which was made by Napoleon Bonaparte, where when he used to send his spies out to find out where the English were setting traps for them, he'd ask them to give me a sketch. It's better than a long speech. So again, a picture is worth 1,000 words is what we often say in our English language today, but that's the history of it. So what we ended up with was basically a graphical system that was a mess. Poor use of colours, colours being used to highlight the wrong things, like in the right-hand side of this graphic I've got here, you're seeing the heat exchangers in bright yellow, and they stand out in the graphic and they take your eyes to them, whereas that's the least important thing on the graphic. There's actually a reactor on this graphic, and basically that should be the thing that's drawing your eye to, not the heat exchangers. And then we saw operators opening multiple screens, and again, the performance of the updates on the graphics was very poor with this number of screens that were open. And navigation was interesting in those days with the graphics like this. A very bad use of colours, overloaded information. And I said to the operator on this left-hand side picture, I said, I can't actually read any of the text on the graphic when you've got all the windows so small. And he replied, neither can I. So a big problem there. So that was one of the issues that we were trying to deal with as we entered into the 1990s and trying to find out solutions for a better human-machine interface. So a poorly designed HMI can degrade the safety, production and quality and profitability, which we've seen numerous examples of in the industry. And we stress that the human-machine interface exists so that process can be run as safely and profitably as possible. So that's our goal. And again, we need to assess at the end of a project, have we achieved that goal? Talked about, we've had a number of incidents in the industry that have been directly attributed to alarm management. and a HMI that doesn't help the operator resolve problems. So basically, our HMIs have encouraged various poor operating techniques, such as running on by alarms, which is a reactive operating stance, actively impeding situation awareness, contributes to higher numbers of avoidable upsets, and increases the likelihood of suboptimal response to an abnormal operating condition. This wasn't helped by the way we actually presented information. They were just basically torn up sheets of P&IDs and put onto separate graphics. And navigation became a nightmare, as can be seen in this particular graphic, how the operator had to get information during a plant startup and the number of graphics that he had to use and basically navigate backwards and forwards to. So it became a mess and very hard for operators to really see what's going on. And they kept asking for more and more screens, even though they couldn't physically see them. They were outside of their peripheral vision. So we had to try and think about, well, what should we do to solve this problem? The other thing we observed was that people were just using color without any discipline at all. And a good example is the use of the color red, which is the brightest color in our palette, and is one that catches our eye and also has some meaning to us. It gives a sense of urgency. Unfortunately, we look at the number of times that the color red was used, and I've seen typically examples of red being used for 13 different things on a graphic. And again, it takes away from the urgent or critical alarm, the priority one alarm, which was the chosen red color. And so basically, we now sort of try to set rules where we say the color is a coding system, and basically we use the brightest colors to get the operator's attention. So those are based on the alarm colors. So we typically have red, yellow, and maybe cyan or magenta as bright colors that we use to stand out on a graphic, and we don't use them for anything else. And then people complain about, well, I like to see whether the valve is closed or the pump stopped, and we use red for that. And we say that color is a coding system, and again, we can come up with a different code to represent those things, and we can get around those issues. So color was the problem, and the other thing about that is that from a human factors perspective, majority of people that are colorblind or color deficient. Basically, these are what they see instead of the traditional red and green that people who have no issues with that color. So basically, it's very hard to distinguish between that basically coding system. And so red and green wasn't a great choice anyway. So we basically put a lot of effort into figuring out other ways of using coding systems to represent different conditions. The other problem we had was the text was too small, or the font was wrong, and we couldn't distinguish whether it was a 5 or a 6 by the type of font that was chosen. So clarity was neglected and lost, readability was diminished and reduced, and mistakes have resulted again in major accidents. So we think about the poor operator and what he was given. And again, this is a recent example of what an operator was using. And he was crammed into this just 4 screens, but basically he had 8 screens typically open just on this console, just by overlaying screens or putting them into smaller squares, which he couldn't really read the details anywhere. The other thing about what happened with graphics was that the vendors tried to demonstrate that they had powerful graphics, and we started to see this visual noise of 3-dimensional piping and a control room in this bottom right-hand corner of this picture, which represents nothing. There's no changing information, but there was a lot of work went into the design of that, which was a waste of time. And if we look at what information the operator actually needs on this graphic, and this is the information, which is, again, poor choice of color and basically too small. and the variable information was just not presented in a good way. So we need to think about that. We need to think about how do we really present information and make it readable and make sure we've got the clarity. This was a good example from a friend of mine, Steve Apple, who basically said, basically, if he was designing a car graphic with his background as a chemical engineer, this is what his car would have looked like. How would you like to drive your car like this? So the question comes, well, what information do we need to drive the car? And of course, the car manufacturers honed in on it and basically said, well, you need a gas gauge, temperature gauge, an oil indication lamp. And basically, all the provided information allows the driver to take action before the car stops through lack of fuel or engine seizure. And so basically, we have what we call a dashboard. So again, that's something we want to think about. We don't want basically a graphic looking like this when really this is what we actually need to drive the car. So again, it gives us the question about, well, what information do we need? We've got a lot of information available. What's actually required? And basically, what does that operator interface look like, which is just a small subsection. The other thing is when we get information, we tend to get it in this format, and this is just an example from Fluffy, our cat, and basically he's got some blood work, and basically we look at the data and we sort of say, well, I have no idea whether the cat is healthy or not. And but this is the way we present information on process information, and we rely on the operator knowing whether the number is a good number or a bad number. However, we can make it a little bit simpler. We can put a reference range, which if you get blood work done recently, you'll probably find that there's a chart very similar to this and an indication of whether one of your conditions is high or low. Sorry? I'm sorry, I can't hear you. If you type your question in chat, we'll try and answer it. So there is a better way of presenting that information, and basically a very quick graphic like this to show that everything's in the normal range is sufficient, and we don't need to go much further than that. But if, again, the information's low or high or going off normal, that's maybe when we want to know more information, physical information, maybe a number. So we introduced the topic of high performance HMI, and as I said, there's something hidden in the wording high performance, meaning it should deliver some form of human performance improvement. What does that mean? Well, if you were a computer, you would sort of say it's characterized by high speed, accuracy, consistency, processing speed, memory usage, response time. And what about from an operator's perspective? What's the performance that we're looking at? And I treat it as their ability to detect a problem, to diagnose it, and to react to it. And good situation awareness will provide that insight by looking at previous information, in other words, a trend, looking at the current information, which may be a number, and then looking at a prediction of where the process is going next by looking at a trend. So we have past, present, and future information that's presented to the operator. We then have the issue of, well, how do we present that information as whether it's good or bad? And basically we have an alarm point, which is indicated by this blue triangle here. And again, basically, if an operator responds in a timely manner, basically we reduce the cost associated with that abnormal condition. Every time we go off normal and into this abnormal area, it costs us money. And if we rely on a second alarm before the operator ever responds, it means we're spending a lot longer time in this abnormal area, which could be stressing equipment, reducing reliability, reducing production, causing quality issues. The cost is obviously significantly higher the longer period we spend in this alarm area. And of course, if the operator misses that alarm, we get the consequence of what we're trying to protect, the alarm was trying to protect us from. So there's some hidden things in here that tell us that, basically just responding to alarms is a very bad way of operating. However, we can, do some better things like basically setting some upper operating limits and some lower operating limits, and basically giving an indication when we're moving from that sweet spot of control to something that's off normal and it's moving towards an alarm condition. We have an example here on the right of dynamic progression, which can be used on a graphic, where basically we're using, this is an example from Lynn Associates, where they use something called bar mode. And when the indicator starts moving to the right or the left, there's some limits. And those are saying that we're moving off normal and into an area which, again, will progress to an alarm condition. And again, the next thing you're seeing here with the 696 is basically it's gone off normal. So we're now showing a number together with the indicator, and you can see how close we are to the alarm condition. And then the next progression is we are actually in the alarm condition. This is a priority 2 alarm. And again, we can see how close we are to the critical alarm condition, the priority 1 alarm. And again, when we get into the priority 1 alarm, how close we are from actually tripping the process out. So that progression is a help that, again, we can give the operator to see how he's progressing up this chart. But I want to focus on these operating envelopes. And again, how do we set those? And again, some people just set them generally to 20 to 80 of the actual operating range. But again, in more scientific ways to actually get some details about where your process actually operates. And again, there are tools available today that can actually provide that information. And if you want more information on that, we'll do it offline. But again, basically, we want to be able to set those operating envelopes and keep the process in this area and get the operator to respond to it before the alarm ever gets in, which again, if we're in normal operations still, it doesn't cost us any money. We start paying money when we cross the barrier into that abnormal condition area. So the abnormal and emergency zones are supported by alarm management techniques to relay information through the HMI to the operator. However, they're not always efficient. While the normal zone becomes part of the HMI hierarchy, the alarm system basically just comes up as an alarm summary display. And often when we get a problem, we end up getting a flood of alarms, which basically overloads the operator. So how do we make the graphics more performant and get this information to the operator in a timely manner? And one of the techniques that we use is what I call perceptual layers. And this is basically where we think about a graphic. And again, when I look at a graphic, I look at where does my eye go to? So in that example I gave you earlier, the heat exchangers was taking my eye to the wrong place. And so what are the zones, if you like, of the perceptual layers? And I think of them like this, basically. Fixed information is just a reference for an operator, so that should be at the very back of the graphic. The next layer on the graphic is standing again in front of that information. And again, if you start using three-dimensional vessels and pipes and start putting bolts and things on things, you'll bring that to the front of the graphic. It's an animation, if you like, almost. So we want to think about how do we push it to the back of the graphic and just make it a reference. The variable information should stand out, and that's basically your process values, if you like. And then we use some different techniques, like, basically here you're seeing the bar mode that Lynn Associates do, and then basically when the needle moves to the extremes of these limits, it throws either replaces the bar with a number, or as I showed you in the example earlier, basically throwing the number out with the bar as well. And basically we can switch from tags to see where the set point is if this is a controller, which it is, a flow controller. But again, we can see where the normal operating range is. And then basically as it moves into an alarm condition, basically we put the color behind the number again, so it stands out nice and bright. And then as we move into the emergency area, again, we have different techniques for showing that, and that should be at the very front of the graphic. So I've got some examples here of graphics. There's one here is with bar mode, and you can see there's one temperature indicator here that's reading high. It's off normal. It isn't into alarm condition yet, but the operator works on that and basically gets it in before the alarm ever comes out. You start reducing the number of alarms he has. We also give the operator the ability to switch between modes, between this bar mode and also the numerical mode. And so basically, again, just a button on the top of the graphic will allow them to see numbers, or very quickly to be able to look at the graphic and see, is there anything off normal on it or abnormal on the particular graphic? And again, these conditions stand out. One of the other nice techniques is here, basically, you can see if it's got a white background, it's indicating it's a controller. Whereas if it's an indicator, it's a duller color. It means, in other words, you can't change anything on it, but you can change things on the controller, such as basically changing the output or changing a set point to make adjustments by pulling up a faceplate. So again, having a graphic that basically is ability to put it into bar mode basically allows you to see anything that's off normal. As you see here, I've highlighted there's one number on the graphic here that's basically showing it that this condition is off normal. And again, we can make changes on the faceplate for it. So again, it's a very good technique. And again, we can other ways of indicating the condition. There's one way here is basically just putting a box around it. I don't like this one as much. There's not enough red. I prefer to see the number highlighted by putting the full color behind the number, which is a lot better. We've also seen a move within the industry by the vendors to replace the quad number of screens with one big screen, a 50-inch screen, and then basically dividing it up into four. And so basically you've got four graphics on one of the 50-inch screens. And again, you can have the same thing on the other 50-inch screen on this particular console layout. I don't like it. Basically what they've done is they've limited themselves. They can't put another big screen above it because you'd have a repetitive stress injury. It would be too high. So basically they try to cram the overview information into this box area that I'm showing here in yellow. And so it's a very limited view of a level 1 graphic. And again, I want to talk about that because as I talk to operators, they tell me that the information up there is just totally useless to them. There's just not enough information. And so basically they're always working on the other graphics, the other four screens within the graphic area. So a better solution, I believe, is this one. And again, when you've got overview screens, it's going to depend on the type of process that you've got. So if you've got a refinery, this can work, but a better solution is to have a video wall where everybody's seeing the common information because the refinery is so interlinked. Whereas if it's a petrochemical process or basically a process, basically like a pulp and paper, this is an ideal solution where basically the operator has an overview of everything under his control, and then basically he can pull down level 2 screens from that overview basically on his desktop. So the ISA 101 basically talks about these levels of basically level 1 is an overview graphic, and then from the overview basically you go down to level 2. So the level 1 is actually split into 4 parts because I've got 4 level 2s here, and then basically from the level 2s we can get all of our level 3s, and from the level 3s navigate to the level 4s. So a typical overview, and this is one taken from a good friend of mine, Mark Rina from Norway, basically showing a production platform, and this is the overview display. And again, it's a large screen, so you can't squeeze that into the top of a 50-inch screen. It's just not possible to get that amount of information in there. And what I like to think about is that, basically, if the top diagrams here are the level 1, basically in green here on the right hand side, I've highlighted the area which is the level 2, And then basically on the desktop, you've got the level 2, and from the level 2, you can go to level 3s, level 4s, and your alarm summary. And so that's the sort of a good number, four screens on the bottom and 2 large screens on the top. But again, we have to really start concentrating to understand, well, what is the information on the level 1 display, and how do we navigate to it from the level 2s and the level 3s? And I've got some examples here, basically of a navigation bar. So the top line here is representative of all the level 2s, and they're extracted from the level 1. And you can see here that I'm going to this level 2 for the CDU overview, I can go down and see all the level 3s, and from the level 3s I can actually navigate to the level 4 graphics. And we can also show alarm conditions, and again, if alarm's been unacknowledged and cleared, we have a way of showing that on the graphic as well. Or we can see here that we've got an active alarm on the crew tower underneath this level 2 CDU overview. So basically on the top line here is all my level 2 screens, and then basically from there I can navigate to my level 3s. We have some different techniques we can use. Basically, information is great when it's in numbers like this, but again, we have to have some alternative ways of showing it because we have so much information on graphics. And again, we use techniques like replacing these temperature indicators with a straight line. And if it's a straight line, it's representing that the temperatures are in the normal condition. And then basically as it bends to the left or the right, it's shown where you've got a cold spot or a hot spot in the actual vessel. And we can switch between these 2 different modes, between a number and a profile. And again, an example of that is shown next, basically, where we have outlet temperatures here shown. And sometimes people put that into a polar star. This one's only representing the inlet flows into the, so again, we can see everything's fairly normal by the perfect shape of the polar star. We're using other techniques, like here we're using the bar mode to indicate everything's normal, and then basically waiting for a number to appear if it goes off normal, and then whether it goes into an alarm condition by adding a color. You can see also we're using these indicators to represent either a value or an analyzer, like this is an O2 analyzer here. Again, a very good way, and again, we're using this shaded area to show that it's off normal or abnormal, depending on how you've set it up. But again, normally if the analyzer is good, it should be up at 12 o'clock, and basically showing a good representation of everything's normal. We're also showing how many alarms are associated in this particular area here from an overview perspective. And again, you can go to the level 3 to get more details on where the alarms are associated with this graphic. So what we've tried to do is we've tried to put data into some form of context, in form of information, to basically help the operator, whether it's good or bad. Because if you've got just numbers like this, it means an operator has to sort of look at it and sort of say, well, is that a good value or a bad value? Is it within the operating range I'm supposed to keep it? And so looking at every number like that is a lot of mental work. Whereas if it's just a trend and it's a straight line, it's a visual indication that everything's good. And again, there's a lot less cognitive work associated with reviewing the graphics. So we have some better techniques today, but again, I think I want to stress that the goal of this is basically for the operator to be able to detect a problem early and do it a long time before the alarm condition ever gets in, diagnosing the problem and then basically responding to it. In the early days of ASM graphics, we identified that we were able to show a 50% improvement in each of these areas of detecting, diagnosing, and responding. And we cut the time down from an operator actually getting a problem to resolving the problem by half, which is, again, tremendous and makes a big difference to the performance of the process. So in conclusion, basically, addressing human factor issues and ultimately eliminating human error is a smart way to do a project. It's often been done by reducing capital costs. This is one of the few opportunities, basically, when you're doing replacement of a control system. And today, most of the control systems are forcing you to reject your old graphics and to do a new project and basically do it from scratch. And it's a good opportunity to do it right and not just copy over all the mistakes that you've had for the past 20 years. It's been converted back over because the operators are familiar with those graphics. Give them something that's good and something that's going to help them from a performance perspective. If you don't do it and you have a major accident, how will you excuse your support of such out-of-date bad practices that don't line up with the standards within the ISA? And I always like what my old friend Trevor Kletz, one of my ICI colleagues from my old days at ICI in the UK, he said, if you think safety is expensive, try having an accident. And again, you just have to go to BP Texas City or one of these other plants that's had a major accident like that, and just look at the costs associated with it, and then start digging into, well, what were the conditions that allowed this to happen? And you'll see in the reports that the HMI is pulled out as one of the contributing factors, together with the alarm management system, and then basically situation awareness in the control room, and basically bad layouts of graphics or no overview screens is often mentioned in the incident reports. So basically, you can look at this and sort of say, yeah, we've been doing things wrong for the past 20, 30 years, and now we have a better idea. There's a lot of good information out there about how to design a good graphic. And don't cheat on the level ones. The level ones should be a good representation of basically the operator's span of control. What's the critical information? I often say to an operator looking at his existing console, and I've seen consoles with 12 and 17 screens, and sort of say to them, why do you want so many screens? He said, well, I need this information. And basically, when you ask him, well, what information on the graphic do you actually look at? And there may be just 2 or 3 different points from each of the graphics, which he still can't see because it's outside his peripheral vision. He could walk to them and have a look at the information on there, but effectively what he's saying is, I need this information in front of me. And often that's a good indication that information may be the type of information you should put onto the level 1 graphic. I also think about it from a perspective of if an operator has a priority 1 alarm, effectively it means that he has to instantly address that condition. There's no time to waste, and it's very critical. And basically, it could be a high pressure in a reactor that's going fast, and before it trips out, we want the operator to try and get there and basically resolve the problem before it actually trips. And basically, we need to see that information standing out on the graphic. And all of your priority 1 alarms should be on the level 1 graphic. So that's a good indication of whether you've captured the right information that's on there. And then basically after the priority 1 alarm is you got your priority 2 alarms, which basically can be up to 15 minutes as a response time. So it's not like the critical respond in 5-minute touch from the priority 1 alarms. But again, you don't want to fill the overview graphics either. You want to keep them fairly simple, but again, making sure that we have the right information on them. And don't get caught by the vendors and try to squeeze your level 1 graphics into this little bar that they've given us in their design. It's pathetic. And again, every operator I talk to basically says it's useless. I never look at it. So there's something wrong with it. And again, if you do design a good overview graphic and put it onto a screen like this, the operators will love it. We've done it in the pipeline industry, we've done it in pulp and paper, we've done it in the power industry, we've done it in basically petrochemical, and then basically we've used it in refining as well. But again, often in the refining, we go more to a video wall these days. Because of all of the interactions that, again, every operator needs to see what's happening on each of the different units because they're all interrelated somewhere. So this is the big issue to me for today, and this is one of the reasons why I offered to do this presentation, is basically to say we haven't got a clue. Every level 1 graphic I've seen that's been done by someone else, or if it's been done by a vendor, is basically trivial, and basically the operators are not using it. If you do it right, the operators will love it. I've heard comments from operators like, now when plan startup, I can see exactly what's going on, and it's a lot smoother startup, and I've got the right information actually on the screens. So that's the presentation, and I'm open now for questions.
We had one question from Tom Smirtnick. If you want to take yourself off mute and ask it rather than me reading it.
That's fine, Brad. Thanks. Ian, I just caught the second half. I had a prior commitment I couldn't reschedule, but what it sounds like was it was brilliant. Thank you for your time. And it always, when this subject comes up by either systems integrators who want to improve something that the controls engineers or the original system architect created, I always wonder whether are they going to affect alarms, and are they going to simplify alarm reporting or warning reporting, or are they going to basically just load up information and overload the operators with graphics? And you've alluded to some of that in your summary there. But in terms of incident response, which is the biggest pain? Is it alarm overload, or is it graphical information overload?
I think it's alarm overload, and then it's insufficient information on the graphics. And again, if you go back to reading a lot of the reports, like the Texaco Pembroke incident reporting system, it basically said there was a lack of overview of the process, so the operator couldn't really see what was going on. He got tunnel vision, and he was basically just focused on his compressor that kept tripping, and trying to get rid of liquids, and had no idea what was going on the flare knockout drum, and basically he overfilled the flare knockout drum. He did have 2 alarms associated with that flare knockout drum, but it was in a plethora of other alarms, and basically his alarm summary just filled up and just went zip, 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 and basically he missed those critical alarms. However, if the flare knockout drum had been on a priority 1 alarm on an overview, I believe he would have seen it. And again, the whole process is about getting the operator to try and keep that big picture and not getting that tunnel vision and getting focused on just one area. There was an incident at Citgo where basically the operator was focused on restarting a heater, and he completely missed that he was actually causing problems further downstream, which were more critical.
Thank you. So in terms of getting critical alarms masked by not having the right information or insufficient information, as you said, how do you show the potential of early alarms or warnings that could be very significant?
And again, that just to answer that question, it's basically what I've alluded to. We are using some form of indication to represent off normal, and
normal. Sure.
So and again, that's about setting. You can see here these indicators are representing normal operations, and the moment the process goes outside of normal operations, in other words, it goes off normal. It's not an alarm condition yet, but It's telling me here the process value is 139, and it's higher than it should be for keeping it in specification, if you like. And then basically, if he makes a change and basically brings that back into line, that will go back to being a meter. But again, as I said before, we have the ability from the operator to be able to just press 1 button and basically change all of the meters into numbers. And so if he wants to see numbers, he can see numbers, and he can see here by the white backgrounds which numbers he can physically change.
Sure.
So they're controllers, whereas the ones with the darker background are just indicators. So again, very quick identification of yes, I've got a problem here. It's moving towards the alarm condition, and then basically I showed you on a graphic the progression of the alarm here from normal to off normal, showing the number, and from off normal to abnormal, where it's got the priority 2 alarm, which is the yellow condition. And then as it progresses, you can see how close we are to basically getting into this is the red area here, which is the priority 1 alarm. How close is the indicator to that? And then basically if it goes into that condition, we highlight it with red instead of yellow, and we show the number as well. And we can also see where basically the trip point is. So again, that's sort of showing a dynamic progression from an alarms perspective. And that's something that's missing today, because normally we're just giving them the alarm summary display and just basically showing them all over the graphic. But we don't actually show that dynamic progression, which is very simple to do today with the modern DCS system.
Thanks again, Ian. Excellent.
No problem.
Thank you.
Okay, Ian, I have a question on the chat. A couple of questions.
Go ahead.
If you look at the chat, first question I had was on the level 1. I go to the level 1, 2, 3, the displays, where you had the overall graphic up high and a separate arrangement, and then you had the console table with the this one, ergonomic console. Go back. I've had occasion to work on major projects. That one, yeah. Is that normally, in your experience, is that a static graphic on the top there? It's not dynamic, I presume.
Yes, it's static. In other words, you don't navigate on it and you don't call up faceplates. However, because it's closed, you can. Phillips 66 decided that they would allow their operators to navigate up to that graphic and basically call up a faceplate or do some form of automatic navigating down onto a graphic using some techniques, just basically to, if I select this, throw it onto this screen type of thing. So there are ways of doing it with the graphic, but most of the time that graphic is fixed. However, it's fixed for normal operation. If you go into a plant startup, that screen may be replaced with startup screens, or if you were in a condition of shutting the plant down, again, you may replace the normal screens, overview screens, with specific screens for shutting down. And so basically showing isolations and stuff like that, and what's running and what's not running. One of the biggest problems when you get a partial power outage is figuring out what's running and what's not running. And so basically you've got options. You can actually change that screen, but most of the time the level 1 graphic overview will be the one that's always displayed on there. And normally you don't navigate to it, and normally you don't make changes on it. You make changes on the screens on the desktop.
I appreciate that. The occasion I had experience with was similar to your design here, and it's a narrow geographic footprint, but very long, like 12 kilometers or plus, multiple facilities,
right?
Strung sequentially, and the biggest problem was keeping the thing up to date. I kept making changes and trying to keep the graphic up to date. But
continuous improvement process.
Yeah, and then secondly, on the level 2, one thing you didn't bring up, I assume that they use it a lot. Their DCS is pop-ups on a certain area for the controllers or some of the alarms. Just on that level 1, they don't have time to pop down to the next page, down to level 3 and all that stuff. At level 3, it's okay to be, if they have to get in that fine tune, or if they're doing startup, or they want to have to look at it for quite a while, they can bring that screen up or part of the screen up and use it. But sometimes it can all be handled, or many times it can be handled by pop-ups, and that includes the alarm things. And so you do that, and then especially for critical equipment, if you have a graphic of a page, you know what your major pieces of equipment are on that process. The major pumps are the critical things, and maybe a couple valves. That's my comment. And then finally, I would say that, what was the other thing? Okay. All right. I forgot the question. So anyway, that's all I had. Thank you.
Okay. One of the things that I think is important is that when you have an overview, like I'm showing here on this large console, is the ability to move down to the level 2s. And again, on the desktop, you may have multiple level 2s open, but when you actually get a problem in a specific area, you actually focus the level 2 and start showing level 3s and level 4s on the other screens on the desktop.
Oh, I know what my comment was. This is to everybody. My experience was they didn't use the graphic. The graphic was not well developed by the DCS supplier. And so everybody, I couldn't believe it. I walked out there and they had 5 to 10 people in the control room, the operators in training. And they were basically what was on that upper part of the console there. They had the big drawing, the big 4-foot by 3-foot drawing, laid it out over this lower console. They were trying to follow the graphics and the process by paper. I couldn't believe it. That's my final comment.
Yeah. Well, again, if you think back at what we had in control rooms, sort of back in the day, in the 60s and 70s, we had basically a mimic, a physical mimic, which was basically the process flow diagram. And to some aspects, basically, the level 1 is that process flow diagram, and then basically the details is the P&IDs.
Oh, I do have another point. Especially with a facility that has a lot of electrical distribution and stuff, and how to and that basically gets doesn't have its own standalone. Like on a power plant, they would have the burners, the furnace would be on one side of the big long set of panels. Then clear down on the other would be all your electrical and your distribution and your switchgear and all that stuff. And the controls for the major pumps and all that. Two bifurcated into 2 different regions on the huge long panel. And the expectation was there would be more than one operator. The guy that was experienced with the electrical would do the electrical, the guy doing process would do the process side. And finally, that's the only thing I don't know how to. We did that because that was basically a low level down from level 1, or we had level 1 screens, but it'd be off on the right. But the same kind of concept. The process would be on the left sets of screens, and then on the right we dedicate it for the electrical arrangement to 1 lines, effectively the 1 lines for the electrical equipment distribution. Okay, that's all I had.
Okay, just as it reminds me of a project we did up in Washington D.C. on the Potomac River power station, and the vendor had put in 4 consoles because they had 4 boilers, and they wanted to add another boiler, and they said the room's full, we can't put another console in. And basically, I went up there to look at it, and I just sort of looked at it and said, "You've got 1 operator." And you've got 4 consoles, and he moves to each console to affect a boiler. Why don't we have an overview with the 4 boilers on, and then basically have screens that you can basically change any one, so you only need 1 console. And we basically ended up putting the 5th boiler on, and basically on 1 console we got rid of the other 3 consoles, which were absolute waste of time. I mean, just unbelievable why they would put 4 consoles in, for 1 for each boiler, and you could just do it on 1 and just have an overview display to be able to pick which boiler you're working on. So yeah, power plants can be a challenge, but they also can be come out really nice and a lot simpler than the original design, which of course in the old days there was 4 physical panels for the boilers. So the DCS does allow us to do simplification of systems, but on electrical distribution, we've done a number of transmission centers, and again we talk about color coding, and they used to have all sorts of reds and blues and whites and all sorts on the distribution screen. And in the end, we got rid of the colors and we just used line thickness. So the thicker the line was, the higher the voltage. And all of a sudden, we could start seeing the distribution from the HT network all the way through to the low tension network. And it was pretty impressive, and lots simpler and easier to use.
Absolutely. I guess that comes up. I had another experience on the same facility. Heavy lines for process that are important, and then thinner, skinnier lines for stuff that's not important.
Yeah.
To try to segregate it so it brings your eye to it.
Exactly.
So you can follow the process from one side of the screen to the other in a
Yeah.
glance. And they had it all big, thick lines, and all the colors were all, and the big, huge for pumps, and big, huge symbols for tankage and all this. Unnecessary.
Yeah.
Unnecessary. Taking up all the footprint of the screen.
Hey, let's
We've
move
seen
on
it.
to Andrew's question.
Sorry about that.
We're getting down to 5 minutes.
All right.
Unmute yourself, Andrew.
I just did. Yes, thank you for the presentation. It brought back a lot of memories of things that I've seen in the past and decisions that were made in the past. One of the comments I'm going to make on your graphic is one of the things that I threw out from the overview screen, or from most of the screens, is that the instrument tag number, the instrument tag
Yes.
itself, is chaff. You no longer need it. You only needed it if you had to locate a controller, but the full graphic gets you zoomed in right there.
Yeah.
The other thing is, like on some of the screens that I've done, is I would take the graphic of the controller, minimize it down to the MSO, measurement set point output.
Yeah.
That meant a lot more, and then alarming. Depending on type of loop, temperature, well, again, the deviation alarms, but there's process alarms, limits. There's different ways of handling different things, which you have already alluded to. Excellent point. But you do not necessarily invoke all alarms on every single controller. You know,
Kind of alarm
you have a level.
rationalization. Yeah.
You know, on the level, it's the outside, and plus the deviation that makes a difference. Okay, too much information there. Sorry, but the graphics that I've developed, and I agree with you completely that the vendor graphics of vessels and whatever else at chaff, threw those things out, put in basically outlines of vessels, but the process lines were important because if you're carrying vapor, you're carrying liquid, and the navigation from screen to screen, you would follow that flow. Let's say you would have a zoomed in it. You would call it probably a level 2, the overall. Then you get down to an area of a plant. So that's another level. But navigation on the most complex plant, how it might have 2 top screens, 2 top views. Each of those, let's say, having 4 or 6, but you could navigate left and right or follow the streams where the problem was. But you would normally back off to the top view, which gave you the alarms. You know, everything's running fine. It's a key trends. It was borrowed. The concept was borrowing key trends from one of the vendors. You know, that you would make up your own screen, and there's your key trends. That's what you watch. No, it was excellent. I've again brought back a lot of memories.
Good. So just one of your comments about basically the tag number. On the systems that we've been working with and developing, basically we have it so that basically the operator has a choice. He can if it's a controller, he can show the tag number, but as you're right, most of the time the operators don't even know what the tag number means, so it's a bit of a waste of time. So basically you can remove it. We can make the process value twice the size, so that if somebody's looking over your shoulder, they can physically see it easier. Or basically, if it's a controller, you can put the set point in there. And so basically, we allow the operator to choose what he wants to put in that space, whether it's a tag number, whether it's a set point, or whether it's something else, basically. So, giving choices is always a good thing. But again, it comes down to sort of what amount of detail do you need on the level 2 from a lines perspective. And often we have to be listening to the operator to help him understand basically how much information does he need to be able to put the picture together. And that's why I go back to my very first comment I made when I put the first graphic of the old panel. How come the operators knew what it was without having a graphic? They knew every controller and they knew exactly what it did and where it was on the plant. And they were better operators than we actually have today.
Excellent point. I was going to make one other comment that I missed in the beginning. Developing graphics, developing overall strategy requires a lot more than just a programmer doing a screen and doing a template. The process flow, the process, what the process is being run, what's important and what's not. But the other is control strategies. If the control strategies are unstable, the operator is doomed.
Yeah.
You have to stabilize the process. You have to make it work.
Yeah. So when I do a task analysis, I like to have a process engineer available. I like to have the control engineer available, and I like operators to be available. And then basically I bring in a sort of a human factor part to it. So basically, as a team, we develop the graphic together. And again, we've gone through the stages where all the graphics were done just by process control engineers. All the graphics were done just by operators. We never found the sweet spot. And the sweet spot is it should be done as a team. And again, you can very quickly develop the graphics. I do them in sketches first, and then basically run them by all the operators on shift, and before we actually start building the graphic.
Okay, excellent. And again, my counter to that is I've been in a lot of plants, and a lot of times the operators only know what they know. They have not gone beyond their boundaries. So
Right.
a certain thing is run a certain way, and it's all that it is. They don't look beyond. The other people would. So sometimes you have to introduce a new mousetrap to it.
Yeah.
This process can be done better. I'll back off. Thank you for your presentation.
Very welcome.
Hey,
Any other
Ian,
questions?
I had a couple questions here. One, first off, your co-author on HP High Performance HMIs had some graphics from Garmin glass cockpits that they use for general aviation avionics, GPSs. You briefly comment on how you think Garmin's graphics were designed, or if they could be improved. There's a lot of information on those glass cockpits. And then secondly, how does ISA S18 and IEC 62682 alarm management standard, and then again then IEC let's see 63303, the ISA 101 standard, how do those dovetail more or less? Obviously 101 and 63303 dovetail perfectly into high performance HMIs, but how does the 818 62682 alarm management standard come in? Because you talked a lot about alarms, and so have they fully adopted the HMI, the high performance HMIs, into those standards?
Yeah, they're harmonized. I think there's no issues between them. Basically, one of the things about when you look at 101 or 18, it gives you a lot of information, but it's not a alarm management for dummies, right? There's a lot of practical experience still required in actually implementing it. And there's a lot of things that are not in the document that you need to know, right? I mean, basically, if you're writing an alarm philosophy, one of the sections that's going to be in there is the HMI. And the same thing that if you're doing a HMI style guide, one of the sections in there is going to be alarm management, and those two should be harmonized. They should be saying the same things. One of the things that when you get to the HMI side of things for alarm management, it's going to talk about, well, how do you enunciate it? What sort of noises do you make? You know, sort of, do you scare people with a priority 1 alarm, right? Sort of, it's obnoxious. It's like a submarine diving, right? But when you've got a priority 3 alarm that's going off a lot of the time, because that's 80% of your alarms, basically you're using a softer color, you're using a softer sound, and basically that's a representative of that 80% of your alarms. Whereas the 5%, it should be obnoxious and it should stand out, and it should stand out on the level 1 graphics. So, you know, basically, I think they're harmonized from that perspective, and they're great tools. And I'm really pleased that the IEC has progressed now, and we've got equivalents to the ISA standards. But again, with a lot of input from the ISA committee members, and I was one of them who provided some information into those. But yeah, there's I think we've got a good opportunity to understand high performance when you start reading those, but again, it misses out on the practical side of things. And again, I think that's why they've started to do a lot of the TRs, so that basically, you know, you're getting some technical advice which is outside of the standard, which is I think is great. I'm a fan.
And let's see, that was somebody just leaving, putting in the chat. Ramon Brito, thanking you for the presentation. Let's see, any more questions? This recording will be, I will make this recording available. It's on my personal SharePoint, but I will figure out how to get the recording up onto either Ian's website or perhaps just put it on LinkedIn again. So people can watch it after the fact.
Put it on all 3.
And so I guess if there are no more questions, we're dwindling down to only 8 people, but let me look at the people that are in the, let's see. Jorge, do you have a question? Or Russ?
No, sir. Thank you very much. It's very good presentation.
Okay. Yep.
Well, a question. Can you or are you thinking to share the presentation with us?
Yeah, we'll make it available either on our website, Brad's site, and LinkedIn. And if we can get it up on ISA, we'll put it up on ISA as well.
Cool. Thank you.
There is another PowerPoint rather is up on the ISA Construction and Design Division page in the last February newsletter, and but it is slightly different from this presentation. I guess we can probably make this possible to, if anybody needs a PDH certificate for this, 1 hour 1 hour PDH, we can develop, we can send out, I can send out a PDH certificate for that. So Ian, thank you very much. And,
very welcome.
That's been somewhat disappointing. We had 88 people that were invited and accepted, and we peaked out of 10 people, so disappointing.
Sometimes that's the way it goes. People get busy, but
well,
we make the
they wait for the recording, Brad, as you know. They want to watch it there. They register so they can get the access to the recording. So thanks for doing that.
Yeah. So okay,
I gotta go. Cheers.
Talk to you all
Take care,
later.
Tom.
Sva.
So, thanks again, Ian.
No problem.
Yeah,
Anytime. Always
And
glad
so,
to help educate
Ian,
the community.
Ian, this is Andrew. Can I ask a couple of questions of you
Of course.
directly? I noticed that your address is Arizona, and you've been across many different industries, including nuclear. The reactor outside of Phoenix, is that one of yours by any chance? Have you been involved with that?
No, I saw the end result, and my comment was they should read the new international standards.
Okay.
is that Casa Grande?
It's
Is it
it's out
Palo
that
Verde?
way. Yeah, Bella
I don't.
Verde. Yeah. Yeah.
Palo Verde.
Yeah.
No, a friend of mine, one of the controls screw-ups, controls problems that happened was 3 Mile Island.